Okay, good afternoon. Welcome back to our class. Let's continue our lecture for digital control system. Today we will focus more on how to use zero order hole for transforming from the continuous system to discrete system. You can see here block diagram of control system where you have continuous transfer function G of S, and you have digital to analog converter in order to convert the digital samples to be analog signal for your system. Because your system is originally continuous, so you have to convert the control signal from digital to analog, which is continuous. So let's see the graphical representation of control inputs. And here for continuous one, so F here is equivalent to the control input U. So if it's in continuous time domain, each time you generate input, you provide the input to the system continuously. So it means at any point of time you can have the value of u of t in terms of a function, let's say f of t. And then let's see the concept of zero order holes, because in the digital world you need to sample every sample time, sample period, capital T. Let's say 0.1 second from this point to this point, and during this period you hold the value of the control input. So you from the computation of computer, you can compute the level of control input U at here, and then you hold the value in order to supply to your continuous system G. Okay, so you hold value around this period, right? Then you compute for the next value at the new time step here to be at this value, and then it hold the value here. Another concept is first order hole. First order means from current value, from this value to the next value at the value for the next time step. You interpolate it as a line from here, from this point to this point. So interpolate it as a line, a straight line. Then you call this first order hole. So in order to analyze our system, suppose you have continuous transfer function h of s, supposed to call G, right? Yeah, and block here is say G, so just write down this G of s, okay? And I guess we have all G of s. Let me pause this. Okay, suppose you have a continuous transfer function G of s defined by this. Then you want to do the analysis of the response of y of t when you have digital control set up for the control input. So you have a sample computed by computer, and then you have digital to analog converter, and you want to analyze it in a continuous time. Then you apply unit delay. Unit delay. Suppose the sample time is 0.3. So why you need to implement the delay? Because you can see in here, if you draw an average value for the zero order hole here, zero order hole signal, you can see that the average value is around like here. Okay. So it's kind of if you look at the you look at the average curve compared to the gray one, you can see a delay, right? It means the performance of your system would be different from having continuous input, right? So and you can analyze this to see performance. Here how you can analyze using discrete time transfer function. You can transform it into discrete and using zero order whole method. Okay, and this is the code that you can use to transform from continuous to discrete. Okay, continuous to discrete. So you just define numerator and denominator for the continuous. TF is for defining continuous transfer function like here, and then you convert from continuous to discrete. Okay, you convert this G from continuous to discrete by the sample time 0.3, right? And because you don't use the argument option for defining the method, then it's by default it uses zero order whole. Okay? You can either just use these two argument input, or you can add another one, ZOH, same thing. So by default it chooses zero order whole method. What if you want to use first order whole, even though your system actually is zero order whole, but you want to analyze the system to use first order whole? Well, you can see here when you transform from continuous to discrete, you don't impose any delay, because the zero order whole here would imply the delay of the input already, right? And then if you use the continuous one but with delay like this, then you cannot use zero order whole again, otherwise you have double delay. So you can use first order whole method instead, right? So how? So first you define continuous transfer function, numerator here, denominator here, and you impose input delay. It means you are defining this transfer function. After then, you convert from continuous to discrete of this G, right? And with sometimes your sample time can be different from the delay, right? Just in case, maybe, well, the delay is happen from something else, not zero order whole, let's say, okay? And then you want to use first order whole to analyze. Or in this case, you have the effect of delay due to the zero order whole, say 0.3, and then you want to analyze using first order whole, you also use 0.3, also okay. Okay. But in general, the system might has its own delay as well. Yeah, so I think in this case better to give this example and this directly, because we have the delay from the zero order whole, then just use this one 0.3. Another way to use approximation, to transform the transfer function from continuous to discrete, you can also use bilinear or Tustin transformation by approximating e to the st by this term. So how you can have this approximation? If you remember Taylor series, okay, first you change e to the st like this to be e to the st over 2 divided by e to the minus st over 2. Do you agree? Because the exponent of this minus this exponent of this, you have twice, so you have st again, right? And if you use Taylor series expansion, you have this one 1 plus st over 2 plus 1 over 2 factorial st over 2 square and plus 1 over 3 factorial s2 over 2 all cube and higher order term, right? And similarly you have this one, yeah, this is Taylor series, right? This one minor, and then this one plus st over 2 square plus this one minus 3 factorial st over 2 power 3, and you have higher order term. Because most of the time you choose small sample time t, right? And you choose small sample time, then you can approximate this term as 0. Okay? Because, for example, t is 0.1, so 0.1 square would be 0.01. It's 10 times less than this one, right? And if t power a larger number, then it becomes just almost 0. Yeah, so this is approximation using bilinear transformation. You just substitute e to the st by z, and e to the st is approximately defined by this term, and finally you can have s is approximated to be this in terms of z. So everywhere you have s, you just substitute by this function of z, then you can transform from the continuous s domain to the discrete z domain. It's very, very convenient, right? So how you implement it with our setup here? If we have a control system like this, so take time to erase this. You have setups like this. Well, so actually you have digital to analog converter, which is preceded by 0 order hole. Then you, in the continuous time, you transform this one, you impose this one with delay, right? After then you use Tustin or bilinear, right? But in MATLAB you use the term Tustin for the option. Okay, so this is option, continuous to discrete option. Method defined as Tustin, and then you put this option into C to D. Okay, yeah. And I think you can try you can try the to transform from a continuous time to a discrete time using this method, just to get familiar with this kind of transformation. Okay, so in order to use Tustin method, First you impose delay to the continuous transfer function to get this, and then you substitute this term by z to the minus 1, because from this formulation, and then s is substituted by this term, and then you can have transfer function g in discrete time equal to so here here is z power minus 1, and then you implement Tustin method for this term, then you have another function of z. Okay, and then in ITC-DCLab it's easy to simulate it once you have polynomial function for both numerator and denominator. Okay, the next part is about continuous time delay. So in the previous example, you already learned that we consider the time delay is the same as sample time, but in some case, in a real application, the delay can be any finite time, but it doesn't have to be the same as multiple time or sample time, right? For example, let's say we choose sample time as 1 second, but then you have delay like 1.3 seconds. Okay, it does not match the multiple time of the sample time. And so how can we do the analysis for this kind of problem? Look at one example for the mixture for chemical process in some chemical plant. You have a mixture out here, but the control valve is far away. Let's say you have a certain length of tube, so you control to mix between hot liquid and cold liquid here, but the mixture will arrive at the tank at some time later. See, so you have a delay because the input of the tank is here, but what you can control is here, around here, right? Well, yeah, so actually in here the problem of temperature control of fluid in a tank is the same as what I explained earlier. Now I just go directly to the equation. The problem here is very simple actually. Suppose we have the same type of liquid but just different temperature, okay? And then we want to control the output temperature in here. So TE at the tank and TE at the output here is the same, right? Same temperature. And the flow rate of the input here must be the same as flow rate of the output, so that you have always the same height of the tank, right? Okay. So the equation to describe the change of temperature in here is governed by this. What does this say? This means the rate change, it's come from this idea. The rate change of heat quantity in here equal to the difference between the incoming heat and the outcome heat, right? So the amount that heat, the quantity of heat brought into the tank minus the amount of heat out of the tank. So it's the rate of heat, the rate of heat. So the rate of heat in minus the rate of heat out is the rate change of heat inside here. You got the idea? It's very simple, right? So the rate change of the heat, the quantity of heat inside is C times m times TE time derivative like this. This is the rate change of heat inside the tank, and this one is the incoming rate of heat. This one is the outcome rate of heat. Okay, so here you look at the how to say the unit. It's joule per second. This one also joule per second. And if C time m time different temperature would be time delta T. Okay, C time m time delta T, then it's joule. And then you take the time derivative. So it's rate mean per unit time. So you use T dot like this. Then it also joule per second. Okay. Now we want to control the temperature. So just find equation of temperature in the tank. Right. So the heat that is brought into the tank is around here. Okay. So the heat brought into the tank equal to C specific heat, m is mass flow rate times the temperature brought in here. Okay. How about the heat brought out of the tank? Yeah, same formula, but you have TE here. Okay. Well, you may find this formulation is not exact same as what you have learned before. Yeah, actually here they use absolute term, so it means two ways. You can use absolute term, I mean absolute value of heat with respect to absolute temperature, or you can define this temperature with respect to some reference. It's up to you. You can do that. Okay, it's not a problem. Okay, because when you compute this differential equation, you start from the initial condition, and if you use the reference temperature as like 0 degrees C, and the initial condition of temperature that you start, you need to refer to the 0 degrees C as well. Okay. Okay. Now that is about modeling, but anyway, the most important thing here is about control, digital control, that you need to focus. The input temperature in here is TE, and this TE is the same as T here in the past. Let's say the time that the fluid travel from here to here is TD, tau D, okay, tau D. So it means the temperature input in here is the temperature here in the time T minus tau D, right? Yeah. Okay, let's say the temperature profile here, let's say it's like this. So let's say here at 2 seconds, and then I draw temperature in here. Yeah, very similar, right? Very similar. But at here, it should be 2 seconds plus tau D, right? Right? Yeah. So if I call this one T, I call this one T. This one must be T minus tau D. Okay? Yeah, I call all of this T, because here is because we write that T dot in term derivative of TE. It means we write something like this. Okay? Yeah. Okay, so the looked EC, yeah, the temperature at input here is the same as temperature at the control here at time t minus tau d, right? So you already understood, I just explained earlier. And then we substitute this into this equation, and this equation is substituted into here, okay, and this one is substituted into here, right? Then we can rewrite t dot e equal this term, if move to the left hand side, you can have plus, okay? This minus, and you have just some coefficient, just call it a, and you have te here, right? So te, and then you have same coefficient a, but you have tc, tec at time t minus tau d, okay? Now we need to do analysis on this equation. Then we can use the Laplace transform, which is to find transfer function. Yeah, meaning that the ratio of output Laplace transform and input Laplace transform. Okay, so we got this first order transfer function, and then we apply the z transform into this transfer function. Okay, but also we use a zero order whole, right? Why this is zero order whole? Because this value is very special. If you move a little bit to the up, okay, whatever, no need to worry about the value. It's zero order whole because before you update the temperature from here to here, the water inside this tube, it has the same temperature, so it's kind of whole, right? And so the temperature flow here is same until from here move until to here, so you have all same temperature, same amount of heat, we can also say like this. So you have zero order whole in this case. Okay, then we apply zero order whole, and then we have this term, and then this term is the same as here, you have seen before. And then what can we do? For the case tau d is not multiple time of t, so we denote different other parameter. L is integer, and is not integer. Is less than 1. Why we do this? To give you the a good way to understand this. Let's say tau d equal to 1.7 seconds and t is 1 second. So what is the value of L? L should be 2. L equal to 2. So you have tau d equal to L times t minus time t. But t is just 1, right? 1. T is just 1. So what is value of m? So L is 2. Should be 0.3, right? So you have 1.7. Okay? This is the idea. So again, L is integer and is less than 1. Then we can write tau d as this, and then substitute tau d into our transfer function here. You can split, because this is you can split the exponent to be like this, and then you some part can be transform into the Z domain directly like this, and then you still have this part. What can we do with this part? We can break down into canonical form, and then we can use Laplace inverse to get the response in time domain. Okay, and then we do the sample. Okay, we sample this. This one is just step like this one. This one is exponential like this one. But because the time inside here is t plus something, so if you, and this one is a step function, right? Step function say if the input argument is negative, which means this side, then the value is 0 like this, right? When the internal in the argument value is 0, it jumps to 1, and when the argument is positive, it always 1 like this. Similar to because here you also have step behind here. So actually you have exponential like this, the original exponential like this, but you multiply it by step which is 0 like this, and then it jumps to 1 like this, right? So here all value here multiplied by 0, you have 0 like this, and then you jump to the value of exponential, and the exponential term becomes like this. Okay.
Well,
so from here we can look at the table to find the Z transform. Yes, step actually is still the same, because step here or step here would be still the same, because for a Z transform we only consider from 0 to infinity, right? From 0 here. So this one we also just consider from here to here, right? Okay. So this is how we can analyze we can analyze the system with delay in the discrete time domain, right? So once you have the value of transfer function in discrete time domain, you can easily simulate the system, right? Is there any question? Okay. All right. Yeah, again, it's easy to simulate it in MATLAB. You can easily impose delay, right, to the system. Let's say TD of 1.5, for example, and when you analyze the discrete time using sample time 1 second, you just input it in here. Okay, but in Scilab it's not so easy. You need to do manually for some part, and then you can simulate once you already have the transfer function in the discrete time like this. Okay, so I want to break for this part. Let's have a break about 5 minutes.